everyone, my name is Hao Wu. I'm going to present our work, EPMA, Efficient Partial Message Access in IoT Era. This is a agenda for this talk, and I will first give the background and motivations, and then I will analyze the problems which will be solved, and then I will provide the solutions and the implementations, and finally, evaluation and conclusions will be given. And this is a vehicle IoT system, which consists of different vehicles on the road and cloud servers. In order to achieve the vehicle intelligence, the vehicles are normally equipped with different sensors, such as cameras and lidars. And all these sensors generate a lot of data, such as images. And all these vehicles exchange these data in order to monitor current traffic and predict the future traffic. As the data generated are very large, how to efficient access and process these data are very important for such IoT systems. Let's take a look. IoT node, which could be on a vehicle or on a cloud servers. On such IoT node, there are several components such as sensing, localization, planning, and all these function nodes produce a lot of data. And apart from this functional component, there is one component which is responsible for forwarding the data to other devices or other vehicles or servers. And such component receives the data from other components and do some filtering and modifying, and then transfer these data to the outside of the node. And for such forwarding component, how to access the data efficiently is very important. And let's take a look at one example where the component receives the message, which is images, and then transfers the data from disk to disks. First, the data are received as bytes, and then the bytes are deserialized to see images because the bytes is easy to transmit, and the component should deserialize it as structured messages. And as the component is implemented by Python language, the C message is deconverted to Python messages. For the filtering step, it reads the metadata and updates the data, and then serializes as the bytes before transferring to other disks. During the whole pipeline, we can see that the filter step only accesses the meta part of the message. However, the deserialize and deconvert and serialize will involve the whole messages, which involves a memory malloc and access the memory, which is not efficient. In order to solve these problems, we propose EPMA methods, and the basic idea is we only access the part we need. We really need. And let's look at the pipeline. When the data received by the component, the bytes is memory copied to the C buffer, and for the deconvert part, we only deconvert the meta part. and we get the message in Python expressions, and for the future step, it only accesses the meta part, and after filtering, we only need to update the meta part of the messages, and then we transfer the messages to other disks and other devices. And by using the EPMA methods, we only need to access the meta part of the messages. In order to implement such functions, we modify the ROS2 message parser because message parser provides the message access functions. The input of the parser is the message definition, which is provided by the programmer. This message describes the message structures, and the message parser, after passing, a header file is generated, including the serialized message and the deserialized message. By using these two functions, the programs only can access the whole messages. We change the parser to generate several functions, which has meta and serialized meta and deserialized meta. These functions provides the ability for the component to access the meta part. By using these functions, the forwarding component can directly access the meta part and update the meta part. To evaluate these methods, we conducted two test cases. The first, we measure the online CPU usage to simulate the case that for the running vehicles, the efficiency of the forwarding component. And for the second test case, we measure the offline latency for 1 PB data to simulate that in the cloud server to perceive and process the data received. The case one shows the result of case one shows for the online CPU usage, the EPMA method is able to reduce the CPU usage by more than 80%. And for the result of case two, shows for the offline processing time, the EPMA method is able to reduce the whole process time from 7.8 hours to 3.7 hours. And the results show online CPU usage is able to reduce by 87%, and the offline processing time can be reduced by 53%. So the whole principle for this approach we found is we only need to access what you need. The original ROS2 can only provide the function to access the whole message, and our approach is able to provide methods to access the small part of the messages. And thank you very much.